Okay, so trying to quickly help myself and you what the fragmentation is, and it's a very simple one. So I'm going to look at the pentane and I think hexane, and we leave that heptane for you. So typically what we have when we look at the fragmentation, we see we have a molecules here, and then we're going to lose something. We lose something equivalent of 15. So what does 15 represent? What is the leftover? We see what we're losing 29, we're losing 43, and others. So those lost of 15, 29, 43 represent a portion of molecule is gone. The rest we can see, but these 15, 29, and 43 we cannot see. Let's take a quick look. When we were doing this in the class, I displayed something from the textbook. We said we have a pentane, so the pentane is, if you add pentane, we get 72 for molecular weight. Remember, we only use 12 and 1. Now, if you look at the spectra, you're going to have a spectra or signal for 72 minus 15. We're going to see a spectra for 72 minus 29, 72 minus 43, and etc. Now, the leftovers basically here, after we lose the methyl group, or methyl 15 is a methyl group, we see CH3, CH2, CH2 as a carbocation. If you lose an ethyl group, we see a propane or propyl cation. Then we see an ethyl cation, and then we see a methyl cation. So when we looking at these things, we should go back and think about what spectra, what signal are we going to see. Again, we start with the pentane, right? So pentane is C5H12. So we have 2N plus 2, 5 carbons, 12, 12, 60, 12 hydrogen times 1, 12. And remember, we only use the exact number, 12 and 1. We didn't use the average because that's later on we talk about the different kind of mass spec, but this is a simple mass spec. So we always use the 12, 1, 16, etc. So we should see for pentane, we should see a signal of M over Z. Remember, this is mass over ions, and the ions is what we're going to see. Ion is always, for simple mass, is 1. So we're going to see mass of 57, and mass for 43, a mass for 29, and a mass for 15. Each of these masses came from pentane, but pentane lost a few things. So in the first case, pentane lost a methyl group, We don't see the methyl group, but we see the remaining, which is the 53, 57. Pentane lost a ethyl group, so we see a mass for 43. Pentane lost a mass of 43, so we see a signal for 29. So this 57 and, let me take a look. So a mass of 57, 43, and 29 is what we're going to see on the spectrum. And from those numbers, and looking at the loss of 15, 29, and 43, we should sort of make sure that we know we most likely have a pentane. Now, in this sample that we had in the class, we didn't show any signal. So I went to a Japanese database I really like. And in this database that we have both signals. So we have now signals, different signals, many signals. And how these signals, the height of the signals. It's a little bit hard to read it here. I have another slide that go over in more accurate sort of version of that. So here's what I propose to look at it. So we're looking at propose as a signal at 43 m over z, and that is 54% height. Then we have a signal at 57, which is 100% height. And we use, that's the highest signal. This one here, 57. Then we have the 43 here. Then we have 86. So if you look at hexane, so hexane is basically 6 carbon, 6 times 12, 14 hydrogen, again 1, so it's 86. So we see 86 here. So we see 86 here. We see a little 86 plus 1, 87 here. And later on, we're going to talk about that. Now let's go back to 86. So 86 basically is falling apart, losing 15 again, losing 29, and losing 43. So these are the three I want to choose, the simple ones. So 15 is methyl group. So we lost a methyl group here. We made a fragment at 61 m over z, the mass, 61, mass 61. Do we see that? No, I don't see that. So then what methyl group is left or not, we don't really see that. But we see the signal after that. If you look at 86 minus 29, which is the ethyl group, 57. Oh yeah, we see that. The signal is pretty good here, 57. That's 100%. Then we see an 86 minus 43, 43. Is this 43? Yes. So that's really the signal we see here at 43. My little arrow went over. So this is 43. We can count 40, 41, 42, 43. So that 43 represent hexane losing a propyl group to make a signal at 43. Now, if I don't know it's a hexane, but I know it's 86 molecular weight, and we look at this pattern, so we can say we lost a 29 and a 43, and other ones we can do, and that made it into hexane. So we can go backward, look at the signal, and decide these signals represent a fragmentation of hexane. Fragmentation of hexane. The next thing I'm going to ask, and not going to put it here, is heptane. Let's look at the heptane, and I'll put that in a little separate paper for you to look at heptane. Okay? Thank you.